Hi, my name is Sangeet Khemlani, and I work at the AI Center at the Naval Research Lab in Washington, D.C. And I want to start off by thanking Molly Quinn and Mark Keene for organizing this fun symposium and for inviting me. So I'll be talking about incompleteness in explanatory reasoning. And I should say this is work spearheaded by Joanna Corman at Bentley University. So much of what I'll be talking about concerns studies that she designed and data she collected. So let me start off by describing two mystifying real-world situations. The first takes us to a forest in Kaliningrad. This forest is called the Dancing Forest, where the trees have all sorts of strange, winding, twisting, rather beautiful forms. And so you might ask, why do these trees have these forms? And unfortunately, I have no idea whatsoever. The scientists don't know in general. There are plenty of theories, of course, scientific theories like theories based on caterpillars damaging the pine shoot, strong winds, the idea that these trees were manipulated by humans, to sort of less satisfying ascientific theories like positive and negative energy clashing, and witchcraft and sorcery. But the real point is that there's no known answer for why these trees are twisted this way. And not having a definitive answer, not being able to explain something, is admittedly vexing. Right? There's a name for this phenomenon. It's called the Mary Celeste effect. This is actually our second mystery. The Mary Celeste was an abandoned ship discovered in the Azores Islands in 1872. The ship was fully intact. Sails were slightly ripped. Some barrels of alcohol were missing, but otherwise absolutely untouched. And the mythology of the Mary Celeste is complex. People theorized, just like with the Dancing Forest, people theorized everything from, aliens to mutiny to poisoning to sea monsters, lots of different ways of explanations of this phenomenon. And just like the Dancing Forest, to this day, there's no real definitive answer. Again, quite dissatisfying, because as humans, we need explanations for things. This isn't some abstract philosophical point, although, as I'll get to, philosophers of science have formed the backbone of much of our contemporary research into explanatory reasoning. This is a practical point. You no doubt may have heard about the growing recognition for AI systems to be explainable. At present, they're kind of black box machines. We don't know how they do what they do in many specific contexts, and they hide a lot of the important details. They can be fallible in strange and often insidious ways. So really, we need systems to be able to explain themselves. This is something recognized by industry folks, government folks, the defense sector, and by academia. From my perspective, the central reason explanations are important is because they help you cope with life. Explanations help you resolve situations that seem inconsistent, incomplete, or incoherent. Let me substantiate this claim with some evidence. So, in a paper from almost a decade ago, we explored situations like these, stark contrasts, where we presented participants with two conflicting statements. If a person is bitten by a viper, then that person dies, and a person was bitten by a viper, but did not die. You could ask people just a simple question, why not? People spontaneously construct explanations for these conflicts. I like them. They're really interesting and creative sometimes. So people say things like, well, because the person had an antidote, or maybe it was a baby viper, or maybe the person was wearing heavy clothing. By far, my favorite response for these will always be because the person was already dead. So in a series of studies, we presented conflicts like the ones above. But critically, we weren't so interested in explanations like these. We did that in some other studies, but on one set of studies, we were really interested in having participants perform two separate tasks. The first task was this explanation task. The second task was to decide whether the statements were consistent or not. You can't actually ask people to decide consistency because the term is kind of overloaded. It's used in all sorts of ways. So what we do is you ask whether both of these statements can be true at the same time. It's equivalent to asking about logical consistency. So in one group, participants first explained, constructed an explanation, and then decided whether these statements were consistent or not. And in the other group, they first assessed the consistency of the statements and then then constructed some sort of explanation. And we basically counterbalanced. We had two groups for these and counterbalanced the orders of tasks on the trials. Now, we did code up the explanations participants generated. They looked like what you might find in previous studies, but we were really interested in the performance on these problems, on the consistency problems. I should say that as a control and to balance the number of times participants could answer yes or no, we gave participants both consistent and inconsistent problems. So, a consistent problem might be something like, if a person was bitten by a viper and that person dies, a person didn't die. So you might conclude, well, maybe the person wasn't bitten by a viper, or you might conclude nothing. But either way, the statement is consistent. There's no conflict going on there. Right? So here's what you find. So for when participants construct explanations first, or whether they construct the consistency, whether they evaluate consistency first, they are accurate at assessing consistency. Right? Here I'm just showing the accuracy of the consistency task. So decent performance, regardless of whether you construct an explanation or assess consistency. When participants have to assess the consistency of these statements first, they're relatively accurate, right? Most of the time they're accurate. But when they have to construct an explanation first, they are for inconsistent problems, they are no longer able to accurately describe inconsistent problems as being inconsistent. Essentially, what we describe this as is the explanation helps hide that inconsistency. It ends up helping participants make sense of the world, and they no longer view inconsistent statements as inconsistent. So this is both good and bad, and we talk about that in the paper. That's not the point. The real point is that this is an example of how explanations help resolve an inconsistent set of information. We didn't really give them any information on whether their explanation was accurate or not. The point being that explanations help people make sense of the world. Right, so that's part number one. Explanations help you make sense of the world around you. Part number two is that people consider some explanations to be incomplete. For many cognitive scientists, this claim isn't particularly controversial. Some early studies, for instance, this study by Naomi Miyake, investigated how people understand mechanical devices. Many mechanical devices seem kind of simple because we understand their function, like a sewing machine, but in fact, they're rather complex, and what happened in Miyake's studies is that when she asked people to start to understand this, how sewing machines work, they vacillate between thinking that they understand the system and then thinking that there's part of a system that they don't understand, right? So she calls this the iterative process of understanding. In our parlance, for this particular talk, a simple way of putting this is that they vacillate between having a complete and an incomplete explanation. Right, so that's work done back in the 80s. Much more recently, Jeff Zemla and his colleagues explored how people evaluate everyday explanations, and they found something rather similar. So what Jeff did was he went on Reddit, an internet forum, on a section of the website called Explain Like I'm 5. So the point of this subreddit is that people pose questions like the following. If Ebola is so difficult to transmit, it requires direct contact with bodily fluids, how do trained medical professionals contract the disease? Right? So that's the kind of thing that they post. And then others offer up different explanations. Good explanations get upvoted by readers and bubble up to the top. So here's an example of a good explanation. I'm not going to read it all, but given all of our collective experiences in the last year, I'm sure many of you will just anticipate why the explanation is good. The person cited that, doctors go into the battle vastly undersupplied. They're forced to use the same pair of gloves on multiple patients. Infections occur when you take off and put on clothing. So what Zemla and his colleagues were really interested in with these everyday explanations is they gathered up all these explanations and gave them to some participants to evaluate how good or bad they were. Now, what he did was he had that information. Then he asked a separate group of participants to evaluate the explanations in a wide variety of topics, right? So, for instance, a group of subjects evaluated whether the explanation cites some sort of expert, right? Whether the explanation presents something new, and critically for our purpose, whether the explanation was complete or not, meaning whether there are gaps in the explanation. And as it turns out, completeness was one of the few factors that predicts the quality of an explanation. So incomplete explanations are bad explanations. Right? That was Jeff's main point. Among other things, Khemlani neatly showed that the human assessment of completeness is systematic. If it was unsystematic, completeness wouldn't correlate with the goodness of an explanation. So the lesson is, it's psychologically sensible to assess whether an explanation is complete or not. Now, the problem with this is that this may be intuitive for psychologists and for cognitive scientists, but not so for philosophers. Philosophers since Carl Hempel have argued that there's no real sensible way to think about explanations as complete or not. Hempel called the idea self-defeating, right? Because a complete explanation really has to be one that explains all of the aspects of a particular phenomenon, and any phenomenon has infinitely many aspects, so it's really impossible to construct a complete scientific explanation. Many other contemporary philosophers, from Rescher to Railton to others, have echoed the same idea. And in a sense, they're right? Explanations can't ever truly be complete. So then the mystery is, what are people doing when they decide whether an explanation is complete or not? They're systematic, but how would you characterize the process of deciding whether an explanation is complete? So that's what Joanna Corman and I have been focusing on. So let's focus on a single scenario to understand the issues at stake. Right? So consider a situation in which some guy named Rob walks into a forest and starts sneezing. Right? So here's an explanation. Being in the woods caused Rob. So the question is, why did Rob start sneezing? And here's one possible explanation. Being in the woods caused Rob to breathe in pollen, and breathing in pollen caused Rob to sneeze. How is this for an explanation? I would personally think that the explanation is relatively fine, right? And you might characterize it in terms of the causal network that is created over here, right? Being in the woods caused Rob to breathe in pollen. Breathing in pollen caused Rob to sneeze. Again, personally, the explanation seems fine to me. The problem is that you can always elaborate on the explanation further. This is the point that Hempel and Railton and others have brought up. You can add infinitely many antecedent causes. So, for instance, you can say, a camping trip caused Rob to be in the woods. Being in the woods caused Rob to breathe in pollen, and so on, right? So it's that camping trip that caused this thing, and then you can kind of go back in time and reconstruct why there was a camping trip and so on. So you can add antecedent causes, or you can add infinitely many intervening causes, right? All of these, so you can say something like, well, being in the woods caused Rob to breathe in pollen. Breathing in pollen irritated Rob's sinuses, and sinus irritation caused Rob to sneeze. And you can go deeper and deeper down to quarks and subquarks and so on, right? So, and the problem is that all of these explanations seem like complete explanations. So maybe a complete explanation isn't an explanation. So maybe a complete explanation is what it really is an explanation with a particular structure, instead of an explanation that addresses all of the infinitely many aspects of the scenario. With that idea in mind, Joanna and I ran a study where we gave participants explanations that mapped onto simple, fundamental structures that other scholars have focused on in causal reasoning. So what I mean is a causal chain, which is the sort of thing that I described to you before, a common effect structure where both A and B can cause C, and a common cause structure where A can cause both B and C, right? And when we gave these structures to participants, we couched them using a cover story where participants kind of imagined that they were teachers evaluating a student's notes on various types of phenomena. So here's what a trial looked like. So one student provides the following explanation. First, imagine that you're a teacher and you get something like this. So one student provides the following explanation for why hinolus, a type of bird, have hexadrine ions in their blood. So the explanation is, having thin feathers causes hinolus to have slow digestion. Having slow digestion causes hinolus to have hexadrine ions in their blood. Now, notice that a couple things. First, that this structure kind of maps on to the structure of a causal chain. Thin feathers, slow digestion, hexadrine ions, right? The second thing to notice is that we designed the materials of the study so that they could be swapped around to create equally plausible explanations. So, for instance, if we swap this around, hexadrine ions could cause thin feathers, right? So we counterbalanced everything. We counterbalanced and randomized a lot of these to eliminate any concern about the materials influencing participants over the structure. Okay. So we presented these three structures to participants, and we asked them. I should say that the question that participants had to respond to was to indicate. We asked them the question: are these notes complete? Is this explanation complete, or is it missing one or more pieces of information? Is it incomplete? And participants provided an assessment on a Likert scale from 1 to 5. Okay, so when you present these three, causal structures to participants, what you find is that for the common effects, participants tend to rate this as relatively less complete. Common effect structures are less complete. Ditto common cause structures. But for causal chains, participants rated this as relatively more complete than the two, and these differences are significant. So the question is, what would explain this phenomenon? The way we've been thinking about this is in terms of models of possibilities. That is, when you think about a causal chain, it's easy to represent the chain using one mental model, right? One mental model of the possibilities. A causes B causes C, which is depicted in this diagram. But for common effect and common cause structures, you need to think about the different relations between cause and effect using different possibilities. That is, it's possible for A to cause C, and it's possible for B to cause C. Ditto with common cause structures. It's possible for A to cause B, and it's possible for A to cause C. These diagrams represent mental models, which brings us to the central idea of our theory, the model theory. The central ideas are that the model theory argues two things. First is that people assess whether an explanation is complete when they can construct a single model of the different components of an explanation, right? So this should be deemed complete, and statements like, structures like these should, common effect and common cause structures should be deemed relatively incomplete. The second point, a critical addendum to the theory, is that whether the explanation concerns 3 events or 4 events or 5 events really doesn't matter. Elaboration shouldn't affect the completeness by default, shouldn't affect judgments of completeness, because if you were to add, at least in this causal chain, if you were to add a 4th and a 5th, event, it would still be just one model, right? So the second point of the theory is that elaboration does not affect completeness. So let me tell you about a couple other studies designed to test this theory. In a second study, we were interested in comparing causal chains, this time with 4 causes, against diamond structures of this sort, where A causes B and C, and B causes D, and C causes D. So eventually A leads to D, just like with this causal chain. Eventually A leads to D, right? Why diamond structures? Well, some theorists have argued that simple explanations are those that have a shared root cause, right? And in this case, you can see that cause A, in both cases, leads to D. So if root causes are what is explaining completeness, then people should treat these two structures as equivalent. The model theory treats these two structures as different. The chain the chain is represented by one mental model, but the diamond structure requires you to build at least 2 mental models to understand it. So the model leading from A to B to D and from A to C to D. So people should prefer the chain to the diamond structure. And that's what we find in our studies. We gave a study similar to the one before, except using these new structures. People rated the diamond structure as being less complete than the causal chain. So experiment 2 validated the model theory's first prediction. It explicitly asked participants, actually both experiments 1 and 2, explicitly asked participants to evaluate an explanation's completeness, which is admittedly kind of an odd task. People aren't usually, asked to evaluate completeness that way. So we decided in a third experiment, we decided to test the theory, in particular the theory's second prediction, that elaboration shouldn't really affect completeness judgments. And we used a more implicit task there. So we came up with problems with these structures, right? Some of the problems were one model problems, right, with structures, basically causal chain structures, A cause B, B cause C, but sometimes they included two premises, and sometimes they included three premises. So A cause B, B cause C, and C cause B, right? Both of them one model problems. On the other hand, there are other problems that concern a set of relations that have some disconnect, some gap in the sequence. So something like A cause X and B cause C. And so you would need at least two models to construct, to understand this phenomenon, A causing X and B causing C. It's not clear how they're connected. Right. And participants were given vignettes that describe student notes of scientific phenomena, as with previous studies, but instead of explicitly evaluating completeness, they were asked to evaluate whether a summary statement, such as A leads to C, was correct or not. So whether A leads to C was correct or not. This task isn't a direct, explicit evaluation of completeness, but rather an implicit evaluation. People should reject incomplete explanations. Okay, that is what you find. What you find is that the majority of participants accept summary statements of one model problems and reject multiple model problems, as you see over here, right? But really, critically, to test the second prediction, their tendency to accept these one model problems doesn't really depend on the number of premises involved, right? So there's no significance between two premise and three premise explanations. In theory, these three-sentence explanations are more elaborate than two-sentence explanations, but in line with the model theory, elaboration didn't affect participants' tendency to accept those statements. We ran a couple of additional follow-up studies, which we describe in our paper, but let me just sum up what we've found so far. Our evidence suggests that a complete explanation is really one that a complete explanation is one in which participants can construct one mental model of that explanation, right? One mental model is the sort of this maps onto causal chains. So causal chains are really what we think about when we think about the complete explanation. Those are the only things that can be used to map onto a single model. This account helps us account for why people consider some explanations incomplete and why they do so systematically. Both Miyake, Zemla, and many other researchers show that people have trouble assessing completeness. Have no trouble whatsoever assessing completeness and doing so systematically. And I would really argue that, we really need an understanding of why some explanations seem more complete than others, because explanations help you make sense of the world. The faster people can get to a complete explanation, the faster they are to bring order to potentially conflicting, incoherent, or inconsistent information. Let me stop there and once again thank my collaborator on this project, Joanna Corman, and I'll thank you as well as many of the other collaborators in my lab and elsewhere who pushed us to make our explanations of completeness more complete. So thanks for listening, and I'm happy to take questions live.